All right, let's just dive right into this explainer and completely demystify the incredible physics and, well, plumbing that made high-speed mobile internet a reality. Whenever you stream a 4K video on your phone or join a seamless video call on a moving train, you're actually relying on a massive engineering leap known as 4G LTE. So today we're going to break down exactly how this technology fundamentally changed global communication forever.
Now, to make sense of the absolute alphabet soup of 4G, we're going to follow the journey of a single packet of data. We'll start with the strict requirements, look at the air interface and MIMO capacity, move to the E-Node B cell towers at the edge, and finally dive into the evolved packet core.
Section 1. The Ambition. LTE Requirements.
To really understand LTE, we have to look at the inciting incident, which was the incredibly ambitious targets 3GPP set for the upcoming decade. You see, 3G was great, but it was really starting to bottleneck. So engineers were tasked with hitting a massive milestone, pushing the one-way transit time of a data packet down to less than 5 milliseconds to support real-time IP applications. I mean, think about that for a second. To make voice-over IP and competitive online gaming feel totally natural, the network literally had to process, package, and fire data through the air and across the core network in a fraction of the blink of an eye. And to make this a reality, LTE required a massive bandwidth leap. It demanded scalable channels up to 20 MHz to hit 100 megabits per second down and 50 up. Compared to older 3G Release 6 networks, we're talking about a 3 to 4 times improvement in spectral efficiency on the downlink. The goal wasn't just to be a little bit faster, right? It was to squeeze fundamentally more data out of the exact same invisible radio frequencies.
Section 2. Mastering the air interface. So how exactly do we push that much data through the air without breaking the laws of physics or completely draining your phone battery? Well, we use dueling air interfaces. We use OFDMA for massive data downloads from the tower, but we actually switch to SCFDMA on the uplink to save your battery. This asymmetrical design is honestly one of the smartest choices in modern telecom. Because let's face it, the base station has plenty of power plugged into the grid, but your mobile phone definitely does not.
Think of OFDMA like taking a totally chaotic road and dividing it into hundreds of distinct, non-overlapping highway lanes that prevent data from crashing into each other. Each lane or subcarrier is independently modulated, and because they're orthogonal, they don't interfere with one another at all. This provides an incredibly robust defense against multipath fading, which is just what happens when signals bounce off buildings and arrive at your phone at slightly different times.
So, the absolutely crucial point for the uplink is that SCFDMA limits power spikes, which is exactly why your phone doesn't just die in 10 minutes when you upload a 4K video. If we used OFDMA for uploading, the signal's power would wildly fluctuate, and that would require your phone to have a massive, expensive, and power-hungry amplifier just to handle the peaks. SCFDMA smooths out those peaks entirely, keeping the electronics in your pocket cheap and efficient.
Section 3. Multiplying capacity with MIMO.
Okay, so we optimize the highway lanes, but what happens when we need to push even more data without just buying more spectrum? This was the next major hurdle for LTE engineers. They essentially had to pull off a heist against the limits of radio physics, asking, how can we reuse the airspace we already have? Radio spectrum is incredibly expensive. Telecoms pay billions for it. So finding a way to transmit more data in the same frequency band is literally like finding free real estate.
The answer is MIMO, multiple input, multiple output. It basically acts like a multi-level highway, simultaneously bouncing multiple spatial streams to the exact same device. By using 2 or more antennas at the cell tower and 2 or more antennas inside your phone, the network can actually transmit entirely different data streams over the exact same frequency at the exact same time. It's pretty wild.
Now, the catch here is that these extra data layers are limited by the rank of matrix H. This means the antennas must rely on environmental scattering to keep the signals decorrelated and distinct. If you're standing in a completely empty desert, the signals might look too identical to your phone, and the MIMO streams just merge into a single lane. But in a dense city where signals bounce off cars, trees, and buildings, the chaotic environment actually helps your phone differentiate the separate streams of data.
Section 4. E-UTRAN and the E-Node B.
Once our data packet successfully navigates the airwaves via MIMO, it hits the absolute edge of the network, the E-UTRAN. Unlike the clunky 3G architecture of the past, the LTE cell tower, the E-Node B, is heavily upgraded to make split-second independent scheduling decisions without waiting for a central controller. In 3G, towers constantly had to ask a central radio network controller for permission to manage resources. But in LTE, the E-Node B terminates the protocols right there at the edge. Plus, these eNodeBs can talk directly to each other via the X2 interface to flawlessly hand off your connection as you drive down the highway.
Section 5. The All-IP Evolved Packet Core.
From that super intelligent edge, our data packet makes its final sprint straight into the brain of the network. Here, LTE executed the death of the old circuit-switched networks, shifting entirely to an all-IP core, where absolutely everything, yes, even your traditional phone calls, is just dynamically routed data packets. Before LTE, networks literally maintained a dedicated physical circuit for voice calls, kind of like a 1950s switchboard. LTE eliminated that completely. It's just IP packets all the way down.
This all-IP foundation builds a brilliantly simple structure, allowing IP packets to fly across heterogeneous subnets dynamically, keeping the whole architecture completely flat and incredibly fast. Because every single device and node has an IP address, data can just be encapsulated, routed efficiently, and delivered. This is exactly what allows for that massive scale and flexibility, perfectly matching the open architecture of the internet itself.
If we take a bird's-eye view of the system architecture evolution, it's easy to see how the eNodeB pushes your data straight over the S1 interface into the Evolved Packet Core. It is so incredibly streamlined compared to previous generations. The radio network communicates directly with the packet core, which drastically cuts down that physical latency we talked about earlier.
The real genius here, though, is the separation of duties. The mobility management entity handles the complex signaling and security, acting like a traffic cop, and that frees up the SAE gateway to just blast your data out to the internet. By completely decoupling the control plane from the user plane, the network can independently scale. If 1 million users suddenly connect at a packed stadium but aren't actually downloading much, the MME just scales up. If a few users are downloading massive files, the gateway takes the load. It's brilliant.
So every time you experience gigabit speeds on a modern device, just remember the foundational physics and IP plumbing of 4G that made it all possible. Without the shift to OFDMA, the absolute magic of MIMO, and the completely flat all-IP core, our modern ultra-low latency world literally wouldn't exist. Which leaves us with one final, pretty exciting question to ponder. How exactly did these 4G LTE building blocks lay the exact runway needed for the 5G and 6G technologies of tomorrow? Thanks for joining me on this explainer, and definitely keep questioning how the invisible world around you actually works.